All right, everyone, we're going to start on page 201. And this, as a lot of you guys are noticing, this lesson does lead into the hard lesson 4-3. But thankfully, we're going to skip that one for now. 4-2 is talking about similar triangles. And the next lesson that deals with trigonometry, that's one of those words like, what? What did you just say, trigonometry? That just means the study, metry, like geometry, study of right triangles. That's all. It's right triangles. And today we're not going to talk about necessarily right triangles, but we are going to talk about triangles. Do you think triangles are important in math? Yes. Why would it be so important in math? Because it's actually something that is applicable to many disciplines. I look at this building and I'm like, thank you for knowing right triangles, at least for now. And I've told you already, guys, that there are buildings where they had a faulty view of triangles, and you can see that Leaning Tower is not so straight anymore, right? The Leaning Tower of Pisa, and that could have been off multiple factors, but I've seen buildings even built today where after a few years, there's something happening to that building. It's starting to shift, and that's bad because that can be dangerous, and at the least, it's worth a lot of money. So triangles are super important, and we're going to start off with similar triangles. Okay, I need you to define the word similar. Similar. So what do you think similar means? Just think what it means in just language in general. Yeah? Like. It's like something, right? So if I say, and I guess I'll use you guys as an example, Owen's a lot like me. We both like sitting in the back. Right? Do you like sitting in the back, Owen? We're similar. Yeah, we're like each other. Now, does that mean we're the exact same person?
No.
Everything's the same about us? No, we're similar in this respect. So similar in geometry is similar to that illustration. And it's going to be figures that have the same shape. Figures that have the same shape, but not necessarily, and that I'm trying to use these words carefully, not necessarily the same size. And when I say shape, I'm not just talking about like these are both triangles, they're similar. No. They can be like one looks like a smaller version of the other. I mean, like almost to the exact measurements of the angles, which we'll talk about in just a bit. What does it mean, but not necessarily the same size? Not necessarily. Yep.
It means but not exactly the same size.
Okay, it means it's not necessarily, and this is where I'm going to try to define it. They're not the same size. Could they be the same size? Yes, but they don't have to be. So that's why I use the word necessarily. Okay, so I want you to do this now. I want you to draw a couple triangles that are on page 201. Don't draw all those numbers and letters with it. Just draw the triangles. You see that little triangle and then the bigger one? Just draw them. Sketch them on your paper. Yes, sir?
If this lesson is on the similar triangles, we're starting into the next lesson. Would the next lesson be congruent right triangles?
They would be right triangles. Some are congruent and some are not. Yeah, but similar right triangles is what we're going to get into the next one. Okay, and draw them big enough. I know I should have said this just a little bit, but draw them big enough so you can write some numbers. I'm not going to have you write all of that, but a good amount of it. So here's my small one. And some of you are much better artists than I am, than I could ever hope to be. And that's a gift that God has given you. Use it. But Mr. A struggles. Oh, man. Whew. Didn't botch that, I hope. Yes, sir. Yeah, and then make it a perfect, yes. And I figured that out last year at the end. No, on this one I'll keep it like this, but yes, you could definitely use that as a smartboard. But like, for example, with art, my mom, she's very artistic. I'm just like, how did mom get it? And my brother is very similar. I remember he drew things that when I was a kid I didn't really understand, but now I think of it, man, when he was in high school, he was doing all these like sketches. I'm like, that's so weird. I could never do that. I struggle. My stick figures are nasty looking. Your stick figures, like, I'm not kidding. But then I think, should I just give up on drawing then because I'm not good at it? And I think the answer is no. And the thing is, the reason I don't want to give up on drawing is, yes, I lack ability to draw. Case in point. But I can get better as I practice and as I appreciate, oh, look at them do it so well. What do you do that's, you pick up little techniques there and there. But art is a worshipful activity. Because when you do good art, who do you worship? God. You reflect Him. Even if you weren't thinking about Him, unfortunately, you were still reflecting. That's good art. And then you look, wow, who gives someone that talent? It's God. He gives that talent to them, but not to everyone, not to me. Not yet, I think. Okay, anyway. Do you guys have your two triangles here? They should look, they should have, yeah, good. They should look similar, which means they have the same, wow, and I am so sorry. I didn't even write that. The same shape. That's a mess up. I'm sorry. The same shape, but not necessarily the same size. Okay, shape and size do mean a lot in geometry. So here I hope, for the most part, same shape, not the same size. Okay, these are similar triangles, not because of the way I drew them, because of these little facts I'm going to give you, right? Okay, ready? This angle right here is congruent to this angle over there, okay? Does anyone know what the word congruent means? It's related to the word similar. It's a little bit more specific. Congruent. Yes?
Figures that have the same shape and the same size.
Okay, when we get to triangles that have the same shape and same size, those are called congruent. Very good. They'll be the same shape and same size. Those are congruent. But with the angles, I can call them congruent. They're the exact same angle. Do you guys see it in your diagram? What angle do they give us there? 94 degrees. So if you could put, if you could fit 94 degrees there, and then 94 degrees here. Okay. Do you guys notice that little arc that I drew here and here? That's called we call it technically like a tick. One tick. That means that both of these are the same. So if you look at, and they're not doing it for you very well, but here, I draw two ticks here, and I draw two ticks there. What am I saying about those two angles? They are also congruent. Okay, they're the same, and in this case, they're both 56 degrees. 56 degrees. Now, and this is kind of cool. Okay, do you guys remember what the three angles in a triangle have to add up to be? What's that magic number? 180 degrees. In fact, any triangle ever to exist that's a true triangle has to have 180 degrees with the three angles put together. Can you figure out what it is here? How would you figure it out? What would you do, Josh?
You add 56 and 94 together and subtract that from 8.
Okay, and what would that number be?
30 degrees.
33?
30.
30, good. Okay, so I'm going to draw 3 tick marks. I'm going to put 33 right here. And 3 tick marks right here. Oh, yeah. Wow, I really want to say 33. Sorry about that.
30 degrees.
Oh. There we go. 30. And you know what? I was almost going to do it again. Okay, but 30 degrees. Thank you. What should all 3 angles in each triangle add up to be? 180 degrees. That's important for this lesson and the next lesson if we were to do it. So far you got part of it down. Yep.
So you know how you measure it with like the protractor to see how much degrees it is? Is there a protractor that like it goes to decimals? Like it's so close, like will we have to do that?
No. You won't have to get like to the decimal point, but the way to do that is to have like this angle right here, and then you would have to have the little tick marks on that protractor show you decimals, which is really hard because they're just so small. But you could do it. You technically could do it. And there are more advanced. No. I would imagine that there's some advanced protractor where you can do it and it can get you right to the degree, which would be cool. But anyway, yes, thank you for Protractors measure angles, and we're assuming what these angles are. Okay. Why are these two triangles similar again? Somebody tell me. Raise your hand and tell me why they are similar. Hayes.
They have the same shape.
They have the same shape. Do they have to have the same size? No. Could they have the same size?
Yes.
Okay, good. So with the word congruent, and we're not talking about congruent today per se, congruent means they have the same size and shape. They have to have both, but in this case we're talking about similar. Okay, do you notice anything about their lengths? You notice anything about these lengths here and here?
They're like similar. Well,
There's a relationship here. Okay, let's do this. How about let's just mark these three side lengths. So you have 3 millimeters, 5 millimeters, and 6. Just put the numbers. Just so it's not cluttered. So 3, 5, and 6 on this triangle. And then 9, 15, and 18 on this triangle. Yes, sir? What? Wait, no, the proportion was last night's homework. All right, how many of you see the relationship between like this side and this side, which is the same as this side and that side, or this side and that side? What's the relationship? How do you put it in words, Ellie? Like, what would you say?
This triangle is 3 times bigger than this one.
Yeah, each one of these side lengths are 3 times bigger than their corresponding side lengths, okay? That's it. Would you say that was proportional? Wait. Let me say that again. So we'll get this down here. These side lengths are 3 times as big as their corresponding side lengths on the smaller triangle. Wouldn't you say that was proportional? Okay, do you guys see what I'm saying with proportional here? And you're like, kind of. Now, the last thing I want you to add on this are the letters. You see those letters A, B, C, D, E, F. Do you guys see those? Capital. All of them are capital. Go ahead and put them where they belong. I got to make sure I do it right. Because if you mix them up, it'll throw off our illustration. We're talking about 2 different things, which is not good. All right, so please check me. Make sure I put the letters where they belong, and check yourself. So we're not going to say different things here and confuse ourselves. Now, these letters are not they're not, like sacred. That means you could have said A, B, C, but we didn't. We're doing it this way for this example, and therefore we're going to write it that way on that example. Okay, this is what we need to get. This next concept here, corresponding sides. So corresponding sides. Okay, so that's the next idea here. We talked about similar, now corresponding sides. Okay, look at side AC. So you name a segment by its 2 endpoints. So you see this is a segment right here. What are the 2 endpoints? A and C. And you can name it CA or AC. But I'm going to call it alphabetical order AC. Okay, segment AC. And how do you know it's a segment? What little symbol should you draw? Yeah, a line. Just a little, and really you call it a line segment above it. Corresponding sides. Segment AC, that's how I read that. Segment AC is similar to which segment on the big one? Sorry. Okay, you have to say it segment DF. Segment DF. Okay, you got to say it DF. We'll see why we're so picky on things in just a moment. Okay, and you know what? I'm not going to go. I apologize. I'm going to stick to and right now because I don't want to start doing those symbols yet. So just say and. They're corresponding. Okay, does anyone know what corresponds to segment A, B? On the bigger triangle, what corresponds to A, B? DE, segment DE. DE. Get me the third pair. Start with the letter C. How about that? Start with the letter C. Get me that third. Segment CB. Segment CB corresponds with FE. How many of you got FE? for the second one. Good. Man, Mr. A, why are we so picky on the letters and how they go? Does anyone know why? Because we are picky, and I will mark you wrong. But why? Why am I so picky? Yep.
So one of the reasons you AC, and like A, I guess A is kind of going like the line goes up to C.
Okay.
So you'd have to do D, and the line goes up. Like if you did F, then it'd be the opposite way.
Yeah, you see how A is corresponding with that 56 degree angle, and C is with that 94 degree angle. If I switch them up, now I'm saying it's the 94 to the 56 instead of 56 to 94. I'm mixing things up. And that might not mean a lot right now, but it will mean a lot when I start looking at lesson 4-3. Okay, so that's where I want to get it prepared for. Okay, there are corresponding angles. And this, I hope, is very easy, I hope. I hope. Corresponding angles. All right, I don't have my diagram up here, but you should have it in your paper. Which angle corresponds with angle A on the small triangle? Angle D. So corresponding angles, angle A and angle D. Which one corresponds with angle, B? Angle E. And which one corresponds with angle C? Can you guys identify those on your own, you think?
Yes.
That's the goal. If you can identify them yourself. So far, so good. Yes, sir.
Are you super picky on how you write the angle symbol?
No, just so that it looks like an angle symbol, like, this one. Is that a less than symbol? Well, in the context, it should be the angle, but just try to do it as neat as you can and as clearly as you can. Because now that I look at mine, Eli, I'm like, wow, I could have done better. This one's good. I like this one. This one I don't like. Okay. Anyway, all of this is going to lead to that idea of proportions. Okay. So what is the length of segment AC? What's the length of segment AC? So you guys remember what, and you can look at your drawing. So AC is 3 millimeters, right? And I'll just put the number. AC is 3. What was the corresponding side to AC? DF is equal to what? 9 millimeters in that case. Okay. Now, do you notice I did put the bar up top? When you say that a segment is equal to a number, I know that this is picky. I'm not going to be picky on your homework on this respect. You don't put the bar anymore. You're not talking about the actual segment itself. You're talking about its length. So you just drop out the bar. You say segment AC is equal to 3 millimeters or whatever units. So if you put the bar, it's okay. I'm not too picky on that. All right. Sorry?
Why does the segment mean the one?
Yeah, okay, and let me clarify. This is tough. Okay, we're talking about geometry. So when I draw the segment, that's segment DF. But when I describe its length, that's a number. And so they're not technically the same thing, although they relate very closely, right? They relate. And so I get your question. And that's tough. Okay. What was the other segment? AB. What's the length of AB? 6, right? 6. And what is the length of...
18.
Oh, sorry. Corresponding is what? Segment... DE, thank you. DE. And what's that? 18. Good. Do you see the proportion? Ready, guys? Here it is. I'm going to give it with words and with numbers. Okay, so taking that info, I'm going to write it with the segments. AC is to AB as DF is to DE. Just write that down. I'll give you some numbers here. Like the letters, like what? This is a bunch of jumble.
That makes sense.
Okay, what's AC?
Yeah, because they're each 1/2.
3. What's AB? 6. What's DF? 9. And what's DE?
18.
18. Is that a true proportion? Okay, if you know the corresponding sides, and we do, right? We have these corresponding, those corresponding, and you know their lengths, which we put here, then you form a proportion with the two ratios. Now, this is a ratio. Is that a comparison of two numbers? Comparison of two numbers? Is that true or false? True. And you guys can figure it out by cross multiplying. What's 3 times 18? 54. What's 9 times 6? 54. So it's true in many ways. We got that. But is that the only proportion I could have formed? The answer is no. It's no. Watch this. Ready? This is cool. It gets cooler. Okay. I said that, and I'm going to have you guys read it this way. AC is to AB as DF is to DE. Can you guys say that with me? I'll say it with you, and then I'll have you do it on your own. AC is to AB as DF is to DE. Okay, now you do it on your own. AC is to AB as DF is to DE. It's music to my ears. It's beautiful. It sounds great. Yeah, that's cool. Yeah, you get to practice here. Well, hey, speaking of kindergarten, I still get those updates. Your class has mastered 25 kindergarten skills.
Wow.
You get a reward. I don't want the reward.
Was that
All right.
Hayes?
I don't know who it is. I haven't looked it up for a little bit, and we will work on that today if we have time, but not the kindergarten skills. Okay, here's another proportion. Ready, guys? DF is to DE. Oh, not BE. DE. As AC is to AB.
Wait, but that's the same.
What property is that?
No.
No, there's no addition. Symmetric or reflexive. Yeah, so symmetric or reflexive. And reflexive, you see all I did was this? So is that okay to do? Okay, can anyone give me another one? There are more proportions here, and it's pretty cool. Yeah.
AC is to DF as
AC is
AB.
to DF as AB is to DE. Whoa, Benson, that's I didn't say that.
That's the one I saw.
Huh. What's AC? 3. What's DF? DF is 9. Okay. So far I have the numbers with AB. So I have to keep scrolling back and forth. AB is 6, and what's DE? 6 and 18. What?
Huh.
Too many proportions.
Does it work?
Yes.
Is it true? Yes. Okay. You can come up with many proportions here because you see relationships. So in similar triangles, many relationships, but are all relationships true?
I take that as a no.
Wait. No.
No. Like I can say, tell me why this is wrong, guys. I'm going to do this verbally. So if you struggle verbally, think about it. Think through it. Okay. AC is to DF as DE is to AB.
No.
Whoa. I'm going to say that again for those who didn't get it. Whoa. Okay. AC is to DF as DE is to AB. Come on, guys. What's wrong with that? So you're saying that 3 is to 9 as 18 is to...
6, yes.
That's not right?
No.
It's not. So you can't just start making up proportions that are not true. Because these two do not correspond in the same way as these two do. So 3 does not correspond to 9 in the same way that 18 corresponds to 6. It's very close, but not the same. Boom. It's not true. Yes.
So like DF or D, whatever that is, DF as to AC, and then DE to AB.
That works. Yep. 9 is to 3 as 18 is to 6. That works. Mm-hmm. Nice. Okay. Let me get you a definition, then we'll get you some problems here. Does anyone have questions on this? I know that this is not always like super clear right away, but I hope you're starting to think Geometry is about thinking, and that is hard. Yes, ma'am.
How would you do like
Yes, let me give you a definition of similar, and then we're going to do maybe 2 problems if we have time. Similar triangles. Just to make sure you guys know what similar triangles are. We got what similar is, but triangles, just to make it clear. Okay, similar triangles. What's the definition? Look on the bottom, page 201. We've only done 1 page today. Yep, 1 page. But anyway, 201. Can someone read that similar triangles definition? Owen. The bottom of page 201.
If 2 triangles are similar in measure, there's simply a corresponding sides of proportional, and there's simply corresponding angles of
Okay, so here we go. 2 triangles are similar if their corresponding sides are proportional and their corresponding angles are equal. Corresponding angles are equal. And I'll do this for you to help you out. Corresponding sides are proportional and corresponding angles are equal. That's similar triangles.
If it's corresponding sides are proportional, doesn't that make it so doesn't that automatically make it so the angles are equal?
Yes. And that's another geometric proof. But we don't all know that yet. But it's a proven thing. That corresponding sides should have corresponding angles in that triangle. But that's not an implied yet. You'll get to that proof later. Okay, you guys get this? Corresponding sides are?
proportional.
And corresponding angles are? Equal. Okay, does proportional mean equal? No, because if they were, we could make this an easy definition and say they're both equal, but they're not. One's proportional, one's equal. Proportional means they relate in a certain way, and equal means they're the same. Okay, let's look at example number 1. This is actually cool. How do we use this? Like, what do we do with this? I don't know if you've ever, I sometimes wonder, how tall is that? How tall is that? And I'm sorry, that meaning a building, a tree, or that person. I don't know. Okay. How tall is that? Well, what's the way you can measure that? You get a giant ruler, or a ruler big enough to measure that out. But I'm thinking like a building. You could get a big ruler, but you're going to have to scale the building somehow and maybe mark it off every time you go up one. That's hard. You can do it by your eyesight and a protractor. Okay? It's pretty cool. Or you can ask, hey, how tall is your building? Yeah.
Yeah, why would we be carrying around a protractor?
You don't have a protractor? I don't care. If you had a protractor, but here, even if you just had the angle, you can get it. But let's look at example 1. How do you even apply this? So, example number 1. Harper, can you read that for us? Surveyors.
Surveyors normally use instruments to measure objects that are too large or too far away to measure by hand. They also can use the shadows that objects cast to find the height of the objects without measuring them exactly. How can a surveyor use a telephone pole that is 25 feet tall and casts a shadow 20 feet long to find the height of a building that casts a shadow 52 feet long?
Oh my, what a hard problem. Okay, either you have the instruments available like surveyors do. Have you ever seen that stand that they use?
Yes.
I've seen that a lot, especially in constructing stuff around here. They have that. I don't have that. So I can use a shadow and a ruler to figure out what they can figure out a little bit slower, but still effectively. All right. What are you trying to do in this problem? You're trying to measure the height of a building, and you're going to use a telephone pole to do that. So you're going to grab that telephone pole, and see. Okay, no. You're going to look at shadows, which is really cool. Ma'am?
How are we measuring shadows? You're still gonna need the big.
Yeah.
But it's not as hard, hopefully, as like scaling the building and using or dropping that ruler, maybe. I don't know. But anyway, no.
You still need to know your spatial displacement.
Yes, of course. And the displacement, the shadows are helping you out, and where you're related to that building or whatever. So you still have to know that stuff. But it's easier than scaling the building. And you can do it from any distance, as long as you can see that shadow. Okay. There are two objects here. We have a building that we want to measure, and they said there's a telephone pole. I don't know. That's why I tell guys, I struggle. Telephone pole. I don't know. And how tall is that telephone pole? 25 feet. 25 feet. They're standard. They're like you can just figure it out. Like telephone. I don't know what ours are here, but wherever they're at, they're standard. So I can figure it out. And they should be standard, right? Because if they're different, they're gonna have different wires and different lengths of that. So they want to make them standard as possible. But doesn't that telephone pole cast a shadow? And even at noon, because of the way we measure time, even at noon, there's a little shadow there. Just depending on where we're at. But there is a time where it's like there should be no shadow, but there is a shadow most of the time. All right, and that shadow is going to be 20 feet. 20 feet. You guys get that? Okay. You guys see the 20 feet? Okay. The building is how tall? I don't know. It's X number of feet. I don't know. But I do know that the shadow that it casts is 52 feet. Don't these form triangles? Don't these form triangles?
Yes.
Are they similar triangles?
Yes.
And you're like, how do you know they're similar? The way I know that they're similar is that when a shadow is cast, all those shadows are in proportion of the objects that are being shadowed. So what I mean is this, like, I stand next to my wife. My wife is 5'4". It's like that. When the sun is pointing at us, from this direction, I cast a longer shadow than she does. Does that make sense?
Yes.
But those shadows can be related mathematically. And we're going to look at that after lunch. Okay, you guys can go. I got to save this so I don't lose where I'm at. Yeah, after lunch. I'm sorry. Yeah, I can save my document here. And I better do it before I forget. Okay. Thank you, guys. We'll finish this up. Oh, I'll get it after lunch. Thank you, Lambs. I forgot about that. Oh, I said so. Yes, I'm going to say. Yes, sir.
Get me right on this. The reason we have 2 days is because if you mess up on the first day, then you have the second day.
Oh,
Is that
I'm
right?
sorry. I was like, what are you talking about?
Because
Actually, Harrison, there are 7 days to a week. And the reason we have... Oh, wait. Oh, you're talking about tryouts.
I am.
Yeah.
No, it really is just to see more. I just want to see more.
Are you serious?
Yeah.
You know what we're doing?
So you don't like me, Mr. Ray?
Yeah, an idea.
Yeah.
Yeah,
You don't like me,
like
Mr.
we only
Ray?
had maybe an hour to see what you guys are about.
I
so we
played
need
for
more.
5 minutes.
Wait, are you
And I
basing
did
it
so-
on shooting? Because I
Yeah.
passed it the whole time.
Yeah, Mr. Ray.
So
And then we
coach is
didn't have
looking
any
at a
plays
lot of
going.
factors.
All
A
right,
lot of
two
factors.
things.
So
I messed up so much. So
That's
if
one.
What?
That's one.
Okay.
Okay.
And he said